compared to the using helicopters and small aircrafts. Has a lot of advantages. You can do localized inspections, and you can immediately collect the data, and it can be processed very quickly. So there are a lot of advantages you have. Again, the one on the right hand side is our UAV system. In this case is the iBotics X6. Surya is going to talk more about it later. But really the uses of this UAV is really caught up more since 2016 in August, when FAA came up with the new regulations, which actually came up with the guidance policy on how to use them. And there are so many new companies started. There are so many different UAV surveys are being done with the different types of sensors, thermal sensors, hyperspectral, and moisture type sensors. There are so many different things you can collect the data by using UAV platform. So with that brief introduction, let me dive into our research project. This is, like as I mentioned, 18-month project, 0-6944. This is again competitive research project. UTI is the lead, and again the project is really how do you use UAVs and CRPs to analyze the data pertaining to the infrastructure conditions. So we're talking about bridges, pavements, rail corridors, even volumetric. So we have done several different things, which I will show you. And we also feel being, this technology is actually a very objective-oriented approach, and it can really be safe because you could do this, with certain protocols we are developed. You could do this along the highway. You may need some traffic controls depending on if it's a bridge, but otherwise you could conduct your data collection, without interrupting traffic a lot, and then once you collect the data, the rest is, again, you can analyze the data. And the data actually, when we collected, it's pretty reliable. It showed what we have observed with the ground truth measurements. And again, I mentioned quick because it's basically if you could run the analysis overnight, you could get within a few hours, the data collection. Again, depends on the size of the data. If you do miles, it will take a few days. But it's in general, this UAV-CRP, which I mean to say is UAV-based close range photogrammetry technology, is a really objective-oriented approach. So I use in the next few slides, Congress is going to use UAV-CRP. Basically, we are talking about close range photogrammetry with UAV platforms. So as a part of our project, the TxDOT project, these are our tasks. 7 tasks are included. I'm not going to go into individual tasks, as you will talk about it later, and just want to mention that, go to the next task. One of the first tasks we had to do as a part of our research, RTI, a research implementation, research and technology implementations division of TxDOT, is do the value of research. And we had to do the economic values and also qualitative benefit areas. You see on the right-hand side the picture, the images that shows. So there are different material topics. So typically in a research project, we had to do this at the very beginning of our task, the first task, and then we revisit this task at the end, because by that time we have done more work, so there may be a revisit. So in the beginning, we made a lot of initial assumptions, and roughly we came up with $8 research investment as a return of $55. But as we finished our project, we found there are more applications, particularly pavements and bridges. So we updated our final cost-benefit ratio. Again, this is research investment. Is that $1 is $204. That means almost 4 times the multiple applications. In my opinion, this even will go up, depending on the type of projects you are dealing with. And with that, go to the next slide. 2 things we did as a task 2 is we collected extensive literature review. Again, Congress has collected 30 plus state DOTs that has worked on these UAVs. Most of them are doing small, a particular bridge investigation or are collecting some data, that kind of thing. So, but very few structured research like the ones we have done. Basically, we have set 2 panels and then both looked at it. And we talked about different things in this literature review. So it's right now under review by the TxDOT panel. Again, all the laws and regulations are covered as a part of 107 that was mentioned. And then various applications areas were also compiled in this literature review. So this is actually a starting point which actually helped us to go with our investigations. The next one is I think TxDOT has the flight planning rules. They want to develop flight operation manual. Basically, there are several rules here. I'm just going to go one by one, but the more details, you can find them on TxDOT aviation website. It's in draft mode. This is a part of the things actually developed with the TxDOT. And again, as I said, we collected all the, we mentioned a lot of these rules based on UAV protocols and everything that is mentioned there. The rule one is really like, if you can see, increase flight crew safety by locating their operations farther away from the roadway or railway. So you don't want this to be. So some of these rule ones you can see here in the pictures here. If you are on a road, if the in a big truck volume, you want to have your drone operations 20 feet away from the road. Again, depending on the speed limit. Again, if it is a railway track, it's at least 50 feet. Again, these are minimum clearance distances you need to have. The next one is rule 2 is again roadways with speed limit greater than 40 miles. The aircraft will cross the roadway at an altitude no less than 50 feet above ground level. Again, this is something we recommended, again, depending on the speed limit. So this is what is recommended. Rule 3, again, takeoff and landing between lanes of divided highway is prohibited. Basically, you do not want to do any of the operations, particularly the UAV operations of takeoff and landing in between the divided highway. You have to do this on the adjacent of the other side of the shoulders. So the aircraft will not operate within 6 feet of any fixed object, and this is also another rule. And then, working along a road right of way, aircraft is prohibited entering into adjacent railroad without the approval of the U.S. coordinator. And basically, this is the picture that covered that. As you can see, the aircraft is prohibited flying within the railroad. If you are doing road operations, you can do the rail operations unless you get some pre-approvals. So rule 6, again, no aircraft will operate under the deck of an overpass bridge or with traffic lower roadway without an approved traffic plan. This is the one part where we can just fly underneath the bridge. You may need a traffic control, and this again is one of the things we will show you later with some of our work. And I'm pretty sure MnDOT is doing some works on the bridges. So and that is the information is also available for you. So the aircraft will not operate directly above a roadway when vehicles are present. This is an important thing. It's on a live traffic. You do not want to fly at this point. Again, at this point, I would like to ask Congress to come and talk about our aircraft, and then we go into the applications.
Thank you, Dr. Puppala. So this is the platform that we have used for collecting the data. Let me go through the parts that are here. So this has 6 pairs of props as well as motors, which makes it a hexacopter. And it's a very lightweight frame. It just weighs about 2 kg without any payload, and it has ultrasonic sensors as well as the most important part is the gimbal, which is a servo gimbal, and it offers a stable platform. As you can see, the camera is mounted on this gimbal, and this camera trigger helps us in triggering the camera according to a flight plan that is incorporated into the plane. And this geobox will superimpose the location and time details onto each photo that was taken. And this LVP antenna will give you a live relay of the camera view during the data collection, so that it is very helpful during bridge inspection, so that the bridge inspector can guide the pilot to show what elements he is interested in. So, and also the landing legs here. So this is about the platform that we have used. And before collecting the data, we need to perform error analysis, because although we have selected all off-the-shelf products, but we need to check how good they are, that is the compatibility between them. So we checked various objectives under that. Like we studied the variation in focal length of the camera, and we studied the thermal effect on lens, that is the lens might change its characteristics during the field operations as well. So we did extensive research on that, and we studied the nonlinear errors like distortion and all. And also during structure from motion, there are some errors induced. And then we also looked for the resolution and resolving power inside and outside, indoors and outdoors. And all these data have affirmed that we can obtain required accuracy. So that gave us the confidence to move ahead with our field operations. And this is the field data collection procedure that we have followed. First and foremost is laying of ground points, which include ground control points as well as ground checkpoints. Control points are used for building the model, and checkpoints are used for checking the accuracy of the model, which I'll be showing in my next few slides. And then this is the flight plan. As you can see, we devise a flight plan. This is a parking lot, and the flight plan is devised in such a way that there is sufficient longitudinal as well as lateral overlap. And also you can see the waypoints at which the camera is triggered to take a picture. So you can see the latitude, longitude, and altitude, which is uploaded into the aircraft, and the aircraft will deliver the camera at these locations to take a picture. So, and it takes the copter takes the assistance of minimum 6 satellites to autonomously navigate through the waypoints. Let me explain in a much clearer way. As you can see, the drone takes the pictures, and you can see the ground control points laid over the area. And when it moves forward, as you can see, the first photo is taken, and when it moves forward in its flight path, as you can see, the second photo is taken in such a way that there is certain overlap. That is the longitudinal overlap. So when it moves along its flight path, it takes pictures with longitudinal overlap with the assistance of satellites. We can also conduct manual flight, which can be conducted without any flight plan, but you need to have an idea about how many pictures you are going to take per second, or maybe with respect to speed. So that requires more experience. And also at the end of first leg, as you can see, this is the end of first leg here, and it moves laterally and moves again parallelly to the first leg along the second leg. As you can see, when it is done here, it moves laterally, and there is also lateral overlap. So if you consider a point somewhere here, it is covered in 4 pictures, or a point here is covered in 4 pictures compared to this. So this is how we do it. We use the photogrammetry techniques, that is using 2 or more images to estimate the distances and measure the 3D models out of these photos. So as you can see, the photos are taken here, and this is the parking lot. As you can see, the photos here, this first photo is corresponding to this. So we use different softwares to stitch these images and build the models with texture, and also high density dense point cloud models are really helpful in knowing the various characteristics of the infrastructure under inspection. So, and after conducting the field procedures, we analyze it, and we build the models. So after building the models, you need to be sure of how accurate they are. So as you can see, let me explain the nomenclature that I'll be following in my next few slides as well. So this is the top view of the parking lot, and this view is the 3D view of this white rectangle shown in the top view, as you can see. And this is the profile view. If you cut, because it's a pavement, you cannot see the parking. I mean, you cannot see much features on the profile view, but when we move forward, I'll be able to show you more details in the profile view as well. But as you can see, I think you can't see this, but the pink square is the estimated position of the checkpoint. And hi Bob, can I move this? Can I move this?
Can you move that?
Because I don't know, it's hindering the view of you.
Yeah.
Yes.
Try that pin over on the right side.
Okay, I think it should move now.
No.
Take it, drag it.
Okay, it should go off, I think, maybe. So this pink square is the estimated position of the checkpoint, and as you can see, these are the points that we have measured at first, and we input these coordinates, and these coordinates are independent of the model. We don't use these coordinates for building the model. So these are independent. So, and then the actual position, that is, we manually locate the actual position, which is represented by green cross, as you can see. Let me give you a much closer view. As you can see, these are the, of course, this is not a standard ground control point, but it's a parking lot. We were not able to mark those crosses, so we just took the joints, the intersection of the joints as checkpoint, and we have placed this, and as you can see, we calculated the delta x, delta y, delta z between these positions, and it is within 1 to 2 centimeters. So that is very acceptable as of now, and with this camera. So this instilled confidence in the engineer's mind to go ahead with engineering judgments. So with that, I'll be moving forward to the pavement monitoring. As you can see, under pavement monitoring, we can estimate the pavement distress like rutting, cracking, and embankment, slope failures, as well as pavement features, which includes longitudinal slope, cross slope, and also some other IR imagery features. So we can find out the cracking percentage, cracking length, edge distress, and also rutting, longitudinal and cross slope, IRI. Even though the IRI, that will be obtained from this technology, is not as accurate as we get from the lasers, but it is comparable. So we can also find out, using all these features, we can find out the PSR. And we have conducted the tests at these locations and identified these parameters, which I'll be showing in my next few slides. And this is the map of those locations where we have conducted the UAV inspections. This is in Texas. You can see Fort Worth, Dallas. And so coming to this, this is an aerial photo of the pavement. And you can see immediately, this is strikingly evident that this part is distressed. Then you might ask, if we can spot it with the naked eye, what is the necessary of using drones, or maybe the algorithms that we developed. So as you can see, this is a heavily distressed area, but then by using the algorithms, you can also find out that these hairline cracks with time will transform into these. So using UAV, we can find out the distress in a proactive manner. That is, proactive monitoring will help us in planning for preventive maintenance. So the algorithms that were developed in UTA are really helpful to find out these proactively. And as mentioned before, this is the top view of the pavement section, a separate pavement section. And if you see this rectangle, white rectangle, the 3D view of it is provided here. And also, if you cut it here, this is how you get the profile view. And you can see there is a depth here. So we were able to find out the distress parameters, extent of it, that is depth as well as the area, which will be helpful in finding out the amount of material that is required to rectify this distress. And also, the engineer will also be able to know whether the pavement has reached rehab condition or not. So, and normally we go out to field site. Actually, this is a US 82 highway, and we do a mission briefing and as well as safety briefing by TxDOT. And this is the drone that is flying away from the pavement and collecting the data of the pavement, which I'll be showing in my next few slides. So this is where we are flying away, and this is the high quality data that we have obtained. As you can see, this is the top view, and this is the 3D view, and you can see the cones here, and in the 3D view you can see this here, this is the cone. And also in the profile view, you can see the cones which are here. So what we did is, according to ASTO, we defined the wheel paths of both lanes. This is a 2-lane highway, and the direction of travel is in this direction. So we were able to find out the longitudinal slope along this 300 feet section. So along 300 feet section, we were able to place 10,000 points. that is with a spacing of 1 centimeter. So this is the longitudinal slope along those 5 paths, that is the left and right wheel paths of outer lane as well as the inner lane and the center line of the both lanes. So the data that is obtained is normally redundant. You can use it in different ways, that is different attributes can be found out from the same data, so that you don't need to conduct more surveys, which is required for traditional methods. Instead of that, we can just collect the data and analyze it for different parameters. As you can see, I'll show you the 30-meter stretch, and this is how we got the outer lane, inner lane combinedly. And this also helps us to know that mostly the slope of all those lanes are matching, and there is no distress or potholes or anything which can be observed. That if there is a spike here, we would have known that it's a kind of dip or a pothole. And using these profiles, we can also find out IRI. I won't say that it is as accurate as the lasers, that is millimeter accuracy, but this data can be helpful in finding out the bad stretches, because we have thousands and thousands of miles of pavement laid on problematic soils. So what we can do is we can conduct the data using drones, and we can find out the problematic stretches and then conduct the costly traditional methods within those stretches. So that saves us time as well as cost, and it provides safety, because we are not moving, or we are not interacting with the traffic, because as you can see, this is the place where we have flown and the pilot is away from the pavement. And this is the same data. Like I discussed before, we found out the longitudinal slope as well as transverse slope on the same data that was collected once. So as you can see, these are the cones, and this is a top view here, and this is a 3D view. And here you can see the profile view of this. Let me show you. So these are the traffic cones here, and you can see in the profile view as well, this rectangle here. So this rectangle shows you the profile view, and this white bigger rectangle shows you the 3D view. So now, as you can see in the profile view, the pavement marking, yellow edge marking is this, and this is the center line of 2 lanes. This white color can be seen here. And this is the white pavement edge marking on this side. So as the direction of the traffic is this, and this is the shoulder here, so you can see the pavement dipping towards outside, as shown by the green arrows. As you can see, this is sloping away. And we were also able to find out the transverse slope at certain interval, that is at every 30 feet, and if needed, if the DOT or any agency requires it to be 10 feet or 1 feet, we can find out. But the processing will take more time, but this is redundant data. We can find out many more attributes than what we get from traditional methods, as you can see. And when I play this video, you can see when this bar moves, you can see how the pavement slope is varying within that stretch, as you can see this. And also occasionally the cones will appear here. As you can see, when it reaches here, you can see the cones appearing. So that gives you, like, it's showing the how the transverse profile is varying, and we can also see whether that is sufficient or not. So this normally we can check the available transverse slope maybe 5 years after construction and see if it is still required, if it is still maintaining the required standards or not, and prevent the hydroplanning. So as you can see, it's the same data that we have did, and I just want to show you here how detailed the UAV data can be. And you can see these are the rumble strips, as all of you know. And if you don't know, mostly people know it when they sleep while driving. So if we have placed the points on those rumble strips, and you can see the profile view where we were also able to estimate the depths of those rumble strips which are uneven. So, and we also conducted stockpile volumetrics using the drone, and we have compared with the traditional methods. And here is the big wrap stockpile. As you can see, there are two types of wrap material depending upon the complexion. You can see two types of wrap material. This is wrap of the underlying layers where there is less asphalt content indicated by its lighter complexion, and here we have wrap of the top layers indicated by darker complexion. So we were able to delineate them and find out the volume of the stockpiles and give an inventory to the agency. And we also conducted traditional method of finding out the volumes using a differential GPS on this small stockpile, and I'll be showing the comparison in my next slide. So as you can see, these are also other stockpiles. We just collected it within 10 minutes. It's a 20,000 square yard area, and we just completed within 10 minutes, and we get all the inventory. If we have multiple stockpiles, we can analyze it for different attributes. And as you can see, these are some of the sites. We have calculated the volume from UAV, and we have got the volume from traditional methods, and this is the one that I was pointing out before. We conducted a GPS differential, and during the time that we collected the whole 5,500 cubic yard stockpile, which was shown before, the traditional survey took more time to just collect this small stockpile. And you can see the values. 5547 is the value given by the agency, and we got 5552, which is 0.1%. And depending upon GPS, which we have conducted at the field simultaneously, we got 102 and 104, which is like 2.5. And depending upon the safety and also the accuracy and the time, this is very much high accurate. And also it gives
when he mentioned about safety, remember, like sometimes folks have to stand up on these stockpiles, which could be very loose. It could have some kind of minor accidents. So safety is an issue when we talk to districts, TxDOT districts, when they're doing the stockpile volumetrics.
And also these GPS differential methods, normally they measure the coordinates of the points and interpolate the surfaces. But with UAVs, we can find out the irregular surfaces as well. It's not estimating it, it's providing just what is there in the field. So that gives us higher confidence in these values. And we move on to the bridge monitoring. So in the bridge, we have superstructure as well as substructure, and these are the elements that are present, as you can see in the picture. So mostly, if we are conducting a deck inspection or the piers, normally we can use a nadir angle or oblique angle, as you can see in the picture. But then, if we are conducting the underbridge inspection, we need to have a different view, and this drone is capable of holding the camera on top, as you can see. So I'll be showing in my next few slides with the inspection that we have conducted on a new bridge as well as an old bridge. So as you can see, this is a SH360 bridge that we have conducted, and this is a 4K video. I don't know if the video is lagging or not, because this is a high quality video, and maybe the internet connection will also plays a key role in showing you the video. But then as you can see, this is a new bridge. Because this is in research phase, we were able to find out a new bridge to show the agency that the UAV is capable of providing high quality visuals safely. And as you can see, wherever we want, we can just pause it and get high quality pictures. And also the important part of it is the underbridge inspection. As you can see, throughout this inspection, the bridge inspector was able to see just the view that you are seeing now on a screen. So he was able to point out the importance of these PMDF, permanent metal deck forms, and the bridges, bridge beams, soffits. And all these were, and the bearing pads. So he was able to guide the pilot to zoom on to the elements that he is interested in. And I'm pretty sure this is being a new bridge, we are not able to see any rusting, but if it is an old bridge, we can see different efflorescence staining or rusting or bearing pad damage. And as you can see, the pile cap and everything is able to showcase in a nice manner safely. So you can see moisture. This is just moisture staining. If it is an old bridge, you could have seen fluorescence staining, which is problematic. And you can see the pile cap and bearings. And the quality of the picture is in such a way that even if we zoom in, we are able to see the condition of the bearing pads, which is very helpful. And this is another rail bridge that we have inspected in Alpine region, Alpine Presidio near Big Bend. So you can see the top gimbal of the on the drone, and although this drone appears sitting on the ground, but still it's flying. And I'll show you the video in a minute. So yeah, so this is the video of the rail bridge. As you can see, the rotten ties here and missing bolts. And also normally this is 60 feet high and 1500 feet long, and people need to walk on this rotten platform if not for the drone to check where there are distresses and all. So using drone, it not only provides, and even this platform is rotten, so no one is going to know whether it is damaged or not. So it's very dangerous to conduct such operations. So using drones, we can also find out rusted areas, corrosion areas, and also different distresses. And as you can see, the railings, and this is an old bridge which is decommissioned. So maybe in the future, using the data, using drones, maybe it can be brought into service again. So, and this is the beautiful view of Presidio, Texas. So, and also we have partnered with MTRI for these studies, and these are the close-up visuals of that railing, damaged railing, and the missing bolts. And we also conducted few more railway corridor studies, and this is the map of it. As you can see, the Big Bend Park and the washout site rock cut. And we went during 2017 summer. It was peak like to 104, 105 Fahrenheit. So it was fun. And you can see the washout. This is a normal picture that we have taken standing on the ground. And you can also see the aerial view of it. So not only the washout, but also you are able to find out the drainage path that is leading to the washout. So by just knowing these simple things, we can also plan for like providing any measure like a arresting wall so that this doesn't happen. So it really helps in such remote areas. The drone inspections are really helpful in such cases. And this is a railroad crossing, and this is not a single picture. This is an ortho mosaic of railroad crossing, and this is a private property. According to FAA and TxDOT FOM rules, we are not supposed to fly over the private property, and hence we avoided it. And after we have collected the data, we stitched them, and this is the quality of data that you can see. And we were flying at a height of 90 feet, and this is how clear the image data is. And you can also, maybe in this view, you can also, it might appear that the road and the rail line are at same level with the surroundings. But then the versatility of outputs that are obtained from UAV-CRP technology gives you a digital elevation model, which quickly gives you an idea about the elevations represented by the color-coded bar here. You can see this blue color is 781 meters, which is here, and this is in between. So that really gives us that it's the pavement and rail line are above the surroundings. So, and also this is a rock cut site where the rail line is passing through, and we were able to fly like as a civil engineer or any engineer, we need to improvise, right? Because there is no flat surface available. So we took the drone box out and we took off from the drone. So we took a lot of protocols to do that, and we used an additional visual observer for that. But then you normally would like to take off and land on a flat surface because of the wind tunnel effect that is created through these rock cuts. So, and as you can see, we collected the data, and this is a top view and this is a 3D view. And if you cut it here, this is how the profile view is. And let me play you the video. The best thing about UAV-CRP technology is it provides navigable 3D models, as you can see there. And we can also see the debris as well as the stability of slopes, which is important for the operation and maintenance of the rail track. So this is high quality data that we can, and also if you bring out a traditional surveyor or anyone, so it's really unsafe for anyone to climb on these steep slopes to find out the slope of these rock cuts. So this is very safe, and we just collected within like 10 minutes of flight time or 20 minutes of flight time together. So, and also we can do the rock slope stability analysis. We selected few steep sections, and we were also able to find out the slopes. As you can see the lines here, if you cut it here, this is how the rock cut appears, and we were able to find out see in different views and estimate the slopes and see these values can be inputted in any slope software, slope analyzing software, and put the material properties. That will be helpful for analysis of rock slopes. And I would like to ask Dr. Puppala to continue from here.
Thank you, Congress. So as Congress demonstrated a lot of infrastructure application areas with UAVs, we feel there are a lot of benefits, as we already showed the valuable data that could be used for health monitoring as well as proactive monitoring of your infrastructure assets. And again, we feel this information could be nicely linked with the maintenance division with asset management strategies, and also we show that we could get quick results in a safe manner with minimal traffic control that saves money and time. And manual labor is very difficult these days. We have to do everything with a smaller number of crew to do this, and that is something we could do this with this technology. Again, we can also collect these surveys at different time periods, so that will tell you what is happening to the infrastructure with respect to time. I mean, this is probably more important when you have structures where settlement of a soil is a problem underneath the approach slab. That's where you could monitor them. You could use this as a tool to know when to go and see if the wall is moving, all those kind of things. And we do this quite a bit in Texas because we have a lot of moving soils. We have expansive soils which are problematic. We have soft materials near the Gulf of Mexico. That's also a big problem. So this is very helpful. Again, as I said, there are a lot of significant cost savings. Again, the technology has been like in a year or so right now. So we just had a couple of sessions. So we presented there in TRB and also one committee meeting. And we're actually going to do more at the TRB 2019 meeting, which is having a UAVs as a part of their display showcase also. So we're going to be doing another special workshop, not workshop, so special session on UAV applications. Again, I think there are different ways devotees can do. Again, this is something we just mentioned to our TxDOT. One is you could do directly with the vendors, or you can have an internal team to do it. And some devotees have their own internal, UAVs. They do that. And also you can have hybrid approach. You can do kind of give it to a vendor to do the work, and then you still have DOT's oversight on this approach. So this is approach 3. So I think right now each DOT is looking at what makes more sense to them, depending on their dollars and then manual power, needs and all that stuff. So right now we actually suggested these 3 different approaches. Again, I think this is something you have to see. So that I think I'd like to mention, again, this is one of our final slides before we did the bridge project on the Mansfield. We are very close to our campus. And again, we have a lot of TxDOT engineers here helping us with the data collection. And this is a new bridge like Congress mentioned. This is something we just have to go and collect it again. The next slide is going to show, this is, as I mentioned, is a TxDOT research project. And a typical project, you generally have 3 or 4 advisors, but this project has so many cross-cutting applications for different entities within DOT. So we have huge number of folks involved in this project. Again, I'd like to mention RTI, again, Joe Adams and Chris Clancy and Rocio Perez. They all are very helpful with this project. Again, my team, I have Cody. Cody is our FAA certified pilot. He's the one working with the Congress on these things, and Ujjwal is another person. We have several other students are working as visual observers during the field works. So again, it's a nice, interesting work we were able to do, and we just got a new implementation project from TxDOT, which is going to look at several districts training as well as going to sites and do some limited data collection as well. Again, this is my information. Again, I would like to see if you have any, may not be able to answer every question, but please feel free to email us. We'll be happy to reach out to you. Again, with that, I want to thank you for your attention, and again, also want to thank Bob for coordinating this whole thing very nicely. Again, with that, I'll close it, and I'll be happy to answer any questions you may have.
Thank you, Professor. We have one question from Paul. One of the issues we deal with in MnDOT is data storage needs, data retention schedule, and general management of this material. It's not a concise summary medium to store and back up. To translate to a concise storage, a significant human processing effort is required. Has there been any thought to these areas related to drone storage and data storage?
Okay, Congress,
that's a very good question, and I personally face this problem with storage because the model, the data that you collect is like in GBs. Normally, a typical site will give you around 5 to 10 GB depending upon the deliverables. So I do agree that it requires a human effort, especially to manage the storage. And also there are some cloud softwares that will also give you enough storage, which you can find it in internet. So that's a really good question, and yes, it requires human effort.
Yeah, it does, because I think, like some of the processing took Congress overnights to do this thing, and he still has sometimes issues with the computer storage because he crashes every time in the middle of the work, and then he has to redo the whole thing. Yeah, but I think, again, like you mentioned, cloud storage, there are places where you could do that. And actually, while we are doing, we have some drone companies that came to us and they wanted to offer their platforms for the storage. But again, DOT has to see the security and secrecy of the data storage, everything. But there are places where you could do that. And I think some of them have their own internal storage capabilities. Some DOTs are looking at buying some of their own storage. That's a great question.
There's a question in the classroom.
Professor Puppala, my name is Bernard Zaweka. You probably remember me. I'm actually impressed with your presentation, quite frankly, because 10 years ago, nobody could have thought there was a replica for running a lightweight profiler or a high-speed profiler to get right. But what you seem to be getting is like a proxy to IROI. Correct me if I'm wrong, are you subjecting the profile you obtain to the quarter car algorithm to get your quasi-IROI, or do you have another algorithm altogether? Then the second part of my question is with FWD and friction, where you probably need, let me say for now, we need contact with the pavement surface to actually get those responses. What's the future of UAVs? For friction and FWD, polyweight reflectometer?
That's another excellent question. I think I couldn't get everything, but let me mention this one. The question is about the quasi-IRI measurements using this platform. That's exactly what we did. When we looked at our dense point cloud, we were able to see the depressions on the surface, and we thought we could get the roughness, by looking at the thing. So what we did is we basically did the same analysis as IRI measurements, looking at the length and then see the undulations, and that's what Congress was able to do this with an algorithm, and that's he developed. And there was a very good match because that site was done with Profiler a few months before. So there's again a slight time gap between when we collected it. But again, this is one study. We're actually going to do more in this new project we just got. We would like to get multiple and then go to the friction measurements, the different things you were mentioning. To be frank with you, I think there are a lot of things we could do with this technology. And, we're just scratching the surface right now. And I think the more case studies we do, we get better understanding. Again, I don't want to say that we're going to replace the profilers or anything, but I think this could be a tool that could be used as a first screening shot before you can go and do more comprehensive, robust measurements. And again, we thank for your comment.
Are there any other questions, online or otherwise? All right, well, with that, I thank you very much. I hope you'll join us next month for Research Pays Off. And thank you very much, Professor Puppala.
Yeah, thank you. Thank you, Bob, and thanks, Congress, again. Appreciate it. Thanks a lot.